Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We're from Group 29. We'll be presenting on our group project of Structured Programming and System Interfacing under University Technology Petronas of Vertical Farm Aquaponic Greenhouse Project. So, this is our group members. Salifah Hidayah binti Rizali, Ummu Balkis binti Muhammad Syahidan, Arya Ahmad Shah Putra, and our last members is Aiman Hakim bin Nurul Basa. Basically, our project is a smart vertical farm aquaponic greenhouse where it uses sensors and automation to manage irrigation, temperature, and stability of the whole systems, where our goal is to support healthy plant growth while also protecting the pump, fan, and other hardware from the damage. So this greenhouse gives real-time feedback through a clear LCD dashboard, which it makes it more easier for all of the users to monitor the whole systems. So by combining advanced control logic, important safety features, cleaning, signal processing, and a stable power setup, this project shows how automation can make small-scale farming more reliable and efficient.
So I'm going to briefly explain about the flowchart of our coding. So basically, we want to start with the sensor. We want to make sure that sensor of temperature, water level ultrasonic, and the soil moisture are read. And immediately, if either of these reach the emergency mode, we will hit the buzzer, turn off the fan, or off if there is not pressure extreme or high temperature. Then just turn off the pump, buzzer, and LCD display. Repeat, and say finally the extreme environment is good. There is no more emergency environment. Just continue normal mode. Just make sure that after the normal mode, we want to make sure that if there is soil, activate pump, and then if not, just turn off the pump. Also, temperature, if 10°C degree or above, turn on the fan, or not, if there is not less than 10°C, just turn off the fan, display the LCD, and refresh every 500 milliseconds, and loop. So there is two loop on the emergency and the normal mode. Loop, just loop around that. Maybe there is no water level because water level doesn't actually control the pump mechanism, but it controls the pump emergency mechanism. It's all for me.
So hi, my name is Balkis. So basically, for the advanced control logic, I'll start with the flood and drain irrigations. So for this, we are implementing ebb and flow cycle, where instead of watering the plant continuously, the system uses an automated ebb and flow cycle. So this means that the pump will on for 5 seconds and it will flood the grow tray, and then it stays off for 10 seconds to allow the roots to soak and absorb nutrients. So this cycle also exposes the roots to oxygen during the off time, which will help prevent root and promote healthier plant growth. So I'll demonstrate how it actually works. So I put the soil at a dry state and the pump will on for 5 seconds and will off for 10 seconds for soaking. So next, for the temperature hysteresis. So basically, this is a system where the ventilation fan does not turn on and off repeatedly when the temperature is around a single threshold, but instead the system uses 2 degrees Celsius hysteresis buffer. So the fan turns on when temperature reaches 30 degrees Celsius, but will only turns off when the temperature cools down to 28 degrees Celsius. So for the active emergency cooling, in the event of a critical overheat, which is above 40 degrees Celsius, the systems will change into a emergency mode. The buzzer will on, but this emergency mode keeps the fan on to actively cool down the greenhouse, but it will shut down the whole other systems. For example, I put the temperature above 40
Assalamualaikum, my name is Zalifah Hidayah, and today I'll be presenting about the safety and protection of the system. So basically, this vertical form aquaponic greenhouse includes several built-in safety features to protect the pump, fan, sensors, electronics, and plants. The system runs continuously in the background using sensor feedback and non-blocking control logic. So first, pump dry run protection. It is to prevent the pump from burning out, and the ultrasonic sensors monitors the fish tank water level. So basically, if the distance is more than 100 cm, the tank is considered empty and the system instantly shuts off the pump and activates a warning. This is to avoid overheating and mechanical failure of the pump. So it is like this. You can see this one is over the 100 cm. This one is below 100 cm. Next, the sensor fault safety interlock. The system constantly checks whether the sensors are giving valid and realistic readings. If a sensor is disconnected or provides impossible values, the pump and other actuators will not activate. This is to prevent flooding, overwatering, or accidental system operation during sensor failure. Next, emergency overheat protection. So when the temperature exceeds 50 degrees, the system enters emergency mode. The fan stays on to cool the greenhouse while the pump and all non-essential systems are
I'm going to
turned off.
explain the signal processing
A
and
critical
accuracy
alert
for our group
appears
project.
on the LCD.
So
This
in
is
our
to
group project,
protect the
we have
plants and
some problem
electronics
with the
from
signal
heat
reading
damage.
and its accuracy,
This is the temperature.
especially related to soil temperature reading. So for soil, there is soil measure necessary and to prevent from false pump
As you
activation.
can see,
Basically, in the soil there is a case of soil measure reading fluctuate and trigger the pump unnecessarily of electrical noise and unstable analog signal from the sensor
next,
itself.
non-blocking alarm
This
system.
can cause the pump
So
to
the
be
buzzer
activated without
uses milis to create a
easily,
double
and this can
pulse beat pattern
increase
without
electrical
fusing the
usage and the wear on the pump
microcontroller,
itself.
which this
So the
means
solution
that
is
the alarm can operate while
to
the
apply a
system
10
still
sample
reads
average
sensors,
algorithm system
updates
to
the
smooth the
LCD
signal
and
and eliminate
controls
any
motor.
spikes so that
It ensures
average data are
continuous
used and
monitoring
it can
even during
predict
warnings.
real moisture trends
And last but not least,
so that
motor and electronics
no more
protection.
unnecessary pump can be
Both the
activated.
pump and fan
Then
are
temperature reading
powered
errors.
through the L
Basically,
to
LCD
9
display
3D
corrupted
motor
or
driver.
misaligned temperature
This
values, as
isolates
well as
high
inaccurate
current
signal lead
motors
to
from
wrong
the
fan or
Arduino,
pump activation.
preventing voltage
However,
drop,
this is because of the
resets,
fact
and
that extreme
electrical
or
damage.
impossible sensor output
The
during
driver
simulation,
allows safe
which
switching,
is mean that
emergency shutdown,
raw sensor
and
data is
protect
too
the
unstable
board
to
from
be
back
trusted
EMF.
directly.
So
Meaning that
that's all
some
from me.
temperature values to medium of -1
Thank you.
Celsius to maintain stable LCD formatting, as well as this clamp temperature can ensure clear and clamp signals too that will ensure accurate environmental control decisions. This all for my part. Thank you.
Hello, my name is Arya. While my groupmates have covered the sensors and control logic, I will be focusing on the system architecture and the human-machine interface. My goal was to ensure the system is electrically stable and that the user data is readable at a glance. First, let's look at the hardware design. A common issue in simulation project is voltage instability. To solve this, we implemented a dual voltage power rail strategy. We isolated the system into two distinct zones, the 5-volt rail from the Arduino for logic and sensors, and this separate 9-volt battery rail specifically for the actuators. This is the 5-volt, this is the 9-volt. This prevents the high current draw of the motors from causing voltage sags that would reset the microcontroller. Furthermore, we integrated the L293D H bridge driver. It's this. We aren't just using this for the fan, we are also utilizing it as a high current driver for the water pump. This simulates industrial relay isolation, protecting the Arduino pins from electrical feedback. Moving to the interface, we wanted to move away from a scrolling display, which can be hard to read, so I designed a smart LCD dashboard. As you can see here, we are displaying 5 real-time metrics simultaneously. T is for temperature, H is for soil humidity, W is for water level, F is for fan, and P is for pump. We optimized the code to update these values individually without clearing the whole screen, which eliminates the flickering effect common found in Tinkercad. Finally, for immediate visual feedback without reading text, we implemented a traffic light status system. 3 LED lights. The green indicates the system is idle and safe. The yellow is alerts the user that automation is active, meaning the pump or fan is currently running. So let's test that out. The fan is on because the temperature hits above 30. It's a critical error, such as the pump dry run protection or critical overheating. So by combining stable power architecture with a clean non-blocking interface, we've created a vertical farm system that is not only functional, but robust and user-friendly. Thank you.